It's kind of wild when you think about it, but everything around us, the screen, the chair you're sitting in, it's all built from just three tiny, tiny particles. Today, we're going to build an atom from the ground up and really get a handle on the secret recipe for, well, everything. So let's just jump right in.
I mean, it's one of the biggest questions ever, right? What is all this stuff around us actually made of? If you could just keep zooming in and in and in, past the molecules, what would you find at the very, very bottom? Well, the answer is actually way simpler than you might think. And by the time we're done here, you'll be able to draw it yourself.
So here's our game plan. First, we'll meet the three ingredients that make up every atom. Then, we'll learn the super simple rules for how they're put together, which will let us draw them. We'll even learn a cool shortcut that chemists use. And finally, we'll figure out what actually makes atoms tick.
All right, first things first, let's meet the main players. These are the fundamental particles that team up to create every single element we know of.
Okay, so what is an atom, really? Well, think about it like this. If you had a chunk of pure gold, and you could cut it in half, and then in half again, and just keep going, the smallest possible piece you could have that is still, gold, is one single gold atom. It's the basic building block. But what are the atoms themselves made of? This is where it gets awesome. The entire universe is built from just three things. Seriously. Protons, neutrons, and electrons. That's the whole recipe.
And each one has a specific job. You've got your protons, which are positive. You've got your electrons, which are negative. And then there are the neutrons, which, yeah, you guessed it, are neutral, no charge. Now, where they live is absolutely crucial. The protons and neutrons, the heavy guys, are packed together right in the center, in what we call the nucleus. And the super light electrons, they're buzzing around the outside in layers called shell.
Okay, so we've met the crew, but I want to zoom in on the electrons for a minute. Because they're not just flying around randomly like a swarm of bees. Nope. There's a system, a really simple blueprint that tells them exactly where to go.
So these electrons live in specific energy levels we call shells. The easiest way to picture it is like a mini solar system, right? The nucleus is the sun in the middle, and the electrons are the planets, but they have to stick to very specific assigned orbits. But here's the deal. These shells have a strict limit on how many electrons can be in them. And rule number one, this is the most important one. That very first shell, the one closest to the center, can only hold a maximum of 2 electrons. That's it. Once it has 2, it's totally full. Okay, so once that first shell is full with its 2 electrons, we move to the next shell out. And the rule for the next few shells is just as simple. They can each hold a maximum of 8 electrons. So just remember that magic combo. 2, then 8 again. That's pretty much the secret code for building atoms.
All right, you have the ingredients, you have the recipe. Now let's actually build something. We're going to see how to visualize these atoms with a super simple drawing called a Bohr-Rutherford diagram. It's a really easy 3-step process. First, you draw a circle for the nucleus right in the middle, and you just write how many protons and neutrons are in there. Then you draw the shells around it like rings. And finally, you start adding the electrons, but, and this is key, you have to fill up the inside shells completely before moving to the next one out.
Let's do a real one. Let's take aluminum. It's got 13 protons, which means it needs 13 electrons to be neutral. So let's place them. First shell, how many can it take? 2. Okay, boom, it's full. Now the second shell, it can hold 8. So let's add 8 more. That's 2 plus 8. We've placed 10 electrons so far. We have 3 left over, so they just have to go in that third shell. See? 2, 8, 3. Simple.
Let's do one more just to make sure we've got it down. Chlorine. It has 17 electrons. We follow the exact same rules. The first shell gets 2. The second shell gets its maximum of 8. We've used up 10 electrons. We have 7 left. So all 7 of them pop right into that third shell. The final arrangement is 2, 8, 7. It's a predictable pattern every single time. Now, drawing all those circles and electrons is fine, but you can imagine it gets a little messy with bigger atoms, right? So chemists came up with a really clever shortcut that focuses only on the electrons that matter most. This shortcut is all about what we call valence electrons. That's just a fancy name for the electrons in the very last outermost shell. And why do we care so much about them? Because they're the only ones that actually do anything. They're the ones involved in chemical reactions. So a Lewis dot diagram just shows the element symbol with dots around it for each of those valence electrons. Super simple. This actually brings us to a really fascinating question. Like, what does an atom want?
It sounds kind of silly, but they have a goal. And that one goal is to be stable, to be happy, you could say. And for an atom, happy means having a completely full outer shell. So when an atom manages to get that full shell by either grabbing or getting rid of an electron, it's no longer neutral. It's got an electrical charge. And we have a special name for a charged atom. We call it an ion. And this right here, this is basically the secret to all of chemistry. Atoms are obsessed with getting a full outer shell, so they face a choice. If they only have a few electrons on the outside, say less than 4, it's just way easier to get rid of them. And when you lose negative things, you become positive. But if an atom already has more than 4, well, it's so close. It's easier to just grab a few more to finish the set. And when you gain negative electrons, you become a negative ion.
Lithium is the perfect example. A normal lithium atom has 3 protons and 3 electrons. The shells go 2 and then 1. That single lonely electron on the outside makes it really unstable. So what's it going to do? Is it going to try and find 7 more electrons? No way! It just ditches that 1 electron. Poof, it's gone. Now its outer shell is that full first shell. It's stable, it's happy. But it still has 3 positive protons and only 2 negative electrons, which means it has an overall positive charge. It's become a lithium ion.
So that's the big takeaway here. Atoms start out neutral, with a number of protons and electrons perfectly balanced. It's only because of that relentless drive for a stable, full outer shell that they're forced to gain or lose electrons. And that's what turns them into ions. And that kind of leaves us with a final, massive idea to think about. This one simple desire, an atom's goal to get a full outer shell, is the engine behind pretty much every chemical reaction in the entire universe. A star burning, iron resting, the battery in your phone, even the complex reactions happening in your body right now, it all comes back to this. It all starts with tiny atoms just trying to get stable. Pretty amazing.